So let's continue on. What I wanted to cover today first is the built-in Matlab ODE solvers. And so there's a variety of them. They all have pretty much the same syntax. And so I'm not going to get into why you use specific ones, but the one that Matlab recommends for you to use first, because it's the most versatile, is ode45. And so that's one I'm going to primarily use for this class because, as I said, the rest of them kind of follow the same format. You could just plug in like ode23 or like 23TB or whatever. There's a lot of different solvers you could use, and you can go through the Matlab documentation if you're really curious. What I'd rather do is just show you. All right, I just showed you the Euler method. How do you use that? How do you use that method to solve a problem, a first order ODE? And so now I'm going to use this Matlab function, built-in Matlab function, to check my answer. I mean, I'm not gonna plot them even side by side. I just want to show you that way. If you were to use ode45, you get the same response as what we got with the Euler solver, which shows that for that problem, the Euler solver was pretty accurate. What's more, I just want to show you how to use it because it's a powerful tool to learn how to use. And so remember, in the last example, I always told you to rearrange your equation such that your highest order derivative, and that's going to matter when we get into second order equations, your highest order derivative is isolated. And so in this case, that's just going to be, if I go back, dv dt is equal to v applied minus v over 0.2. And so if you remember in the last example, I put that into a function. The reason I did that is because the whole point of putting it into a function is it's easier to call it in the Euler equation, but it's also the way you have to give it for ode45. You have to create a function and then pass that function and say integrate this function, solve this differential equation function over some given t span, and with the initial condition. So like always, you have to give an initial condition, and you have to give it the starting and ending t, or you can give it a range of t values you want to find the solution to. And so I'll show you what the difference between that is here in a moment. And so before I even do anything else, I'm going to reset up this previous function so that we can solve it in ode45. So let me scroll up real quick. So if you remember, you have to solve the equation for dv dt, which I've already done right here. Dv dt is equal to v applied minus v over 0.2. The v applied is this complicated equation, but that's fine. You just plug it in. You just plug it into an equation. That's not a big deal. You're given that RC is equal to 0.2, so I plug that in, and your initial voltage is 2 volts. And so that's going to matter when I actually go and plug it into ode45. But first, let me create this function. So again, I'm going to use a sub-function. I don't want to save this as a function file necessarily because I'm not going to use it outside of this script more than likely, or these two scripts. And I don't want to clutter up my my folders. And so I'm just going to create a function, and that's going to be that'll be the same function I was creating before, where v dot or dv dt is going to be equal to voltage, my function that I'm creating. This is the voltage function, which will be this f of tv, t comma v. And so now I know my dv dt equation is right here. It's going to be dv dt is equal to v applied minus v, and then that's going to be divided by 0.2. But now, as I usually do, I've gotten this equation that I have out here, and I say, all right, I've defined v already. It's in my input to my function, but I haven't defined v applied yet. That's easy enough because it's defined in the problem. It's this value, these values right here. So v applied is equal to 10 times 2 minus e to the negative t times sine of 5 times pi times t. And so remember, everything in my function file has to be defined based on the inputs, and it has been. I just have, this is a function of t, which is one of my inputs, and then this is a function of v, which is one of my inputs. So I've defined this function. Remember, I used that in the Euler equation by plugging it in to this equation here, right? And f is this function I created. Delta t was my time step, and v was my time at the previous iteration. So starting with the initial condition and then kind of continuing on from there. But now it's going to be even more straightforward, is that I can actually just plug this into the ode45 function. So this is my general form. And so let me just show you, how do you plug in that general form. So I'm going to do time v voltage. I'll do v is going to be equal to ode45, and then I'm going to do at voltage, because I need to give the ODE function, which that's this function here, voltage, and use this at sign to say, okay, this is a function handle effectively. This means point to the function that is either in the saved as a file or in this script file that is named voltage. Then I'm going to give it a t span, which is going to be from 0 to 5. Then my initial condition was 2 volts. And that's all I need to do. And now I'm just going to steal my plot from my previous example, because a plot should be the same. And so applying time v, and then x-axis is time, y-axis is voltage. So if it works, it should be the same graph as before. And it does, it works. And if you notice though, it ends up being a little bit choppier because I didn't give it as fine of a time step, right? I just allowed it to use whatever time step it needed to solve the problem, which is what it's going to do no matter what. But I didn't give it enough outputs. And so the way that you can control how many output numbers you get is you can actually, so in this case I used a step size of 0.01. Into the ode45 t span part, I could do 0, 0.1, give it that whole vector of time that I wanted to evaluate. And so this is going to be like a time vector, and it'll output the same amount of voltages. So the voltages that correspond to that time. So let's run it, and you see now it's a lot finer. There were a couple like corners that popped up. What I will say though is it doesn't actually change the solution. The ode45, I think, is a variable time step solver, which means that it comes up with its own time step to get the most accurate solution. And so it did that, and then just applied, basically probably interpolated and plugged in all of these points and got the answer. So this doesn't actually change the time step your solver is using. So for example, it wouldn't have changed. So if you're kind of thinking this is an analog to the Euler, that didn't change this time step that was used. It just changes what your output will be. And so you can give a more refined or a more coarse output depending on what you want. And so that's in a nutshell how to use ode45. It's a lot easier. I mean, but realistically, the Euler equation didn't take that many extra lines. It did. I mean, it took maybe, I have some spaces here, maybe 6 lines. 6 lines instead of 1, but it's still not that complicated. And so what I want to do is show you another example. And my goal in this is going to be, I want to use Euler method and ode45 method to solve this equation. And let me full screen it for you. But my end goal is to predict some certain response. And so the following equation down here, this is a differential equation, describes the temperature of a certain object immersed in a liquid bath of constant temperature. So you have some, let's say it's like a metal ball or something you drop in a bath of water, and the ball is initially at 70 degrees Fahrenheit, so it's room temperature, and then your bath temperature, the water temperature, is 170 degrees Fahrenheit. And so this is the differential equation that would relate those two things. The temperature of the bath is given on the right-hand side, and then the T and dt, T and T right here is the temperature of the object. So what you're doing is you're solving this equation for T to calculate the temperature of the object with respect to time. Because if your object is room temperature, drop it in a hot bath, right? A hot bath of water, or just any liquid. It's going to eventually heat up, right? It's going to eventually actually approach the temperature of the bath right here. And so what I want to figure out is how long does it take to reach the bath temperature? And then, well, if not that, how long will it take for the object to reach temperature 168 Fahrenheit? So a little bit below the temperature of the bath. And then I want to plot T with respect to time. And so I think originally you gave this as like an in-class example and like then worked it for everybody. But what I'm going to do is I'm going to use both the Euler method and the built-in ode45 function. I want to use both of these. So this is a simpler problem than the one prior, right? But I want to show you how to set it up. So the steps for the Euler method, which is what I'm going to start with, is isolate the derivative. I need to find, in this Euler method, I need to find this function that I need to apply for the Euler method, and that is in the form of the derivative equal to some function. So you just rearrange this fairly simple equation for dt. So you subtract by t you subtract t to the other side, divide by 10. It's kind of like an algebra 1-ish equation. Solve for dt. And so you get this right here. T bath is equal to 170, so you could already just plug that in if you want. And so I can plug, this is my function that I'm going to evaluate for each time step. So let me now go and solve the problem. I'll leave this up at the side. So I'm gonna initialize my script right there. Okay, and so now I need to set up my initial conditions. So my time vector, this is part of the question, is I don't know how long it's going to take. I didn't give you the time, and so I want to create my time vector. So first I'm going to define my initial temperature. So T of 1 is going to be equal to 70 degrees Fahrenheit. Oh, I don't need to include that F. So it's going to be equal to 70 degrees Fahrenheit. I'm going to use a time spacing dt is going to be equal to 0.01. I want it to be a really small time step for now. And so I don't know how long this time vector needs to be. I don't know. I know it's going to start at time 0. And I know it's going to use the spacing dt. That's why I created it. But I don't know when it's going to end. So let's do like to 100 seconds. Let's overkill it. Let's see how long it needs to be, and I can always go back and rerun it for a smaller case, right? And so now I need to go through and actually solve this problem. And so remember, I'm going to set up this in a set function at the bottom. That's what I did before, function, because then I can just plug in this exact equation in a for loop and be done. So function, this is going to be dt. So the derivative of t with respect to time is going to be equal to temperature, temp of t comma capital T, right? This is a function of t and time. Technically, it's not even a function of time, which will make this even simpler. But you don't know that. It needs to, the input and output of this needs to be time and temperature. Okay. Easy enough. And now I just plug in this equation. So now I know that dt is going to be equal to tb minus t over 10, and then this needs to all be in parentheses because it's in the numerator. I haven't defined tb yet. I could have just plugged into that equation, but tb I know is going to be equal to 170 Fahrenheit. Now I have this function that's isolated the derivative of time with respect of temperature with respect to time. Wonderful. And now I just need to, my second method here is define the time interval. My second step here is define the time interval, plug it into the Euler method equation, and use a for loop to build the, in this case, t vector. I just copy and pasted this, the t vector. And so I'm going to do for I is equal to 1 to length time. And remember, I have to do length of time minus 1. That's just what you have to do for the Euler equation because I'm going to be predicting the next time step of t. And so once you get to the end of the time matrix, there's no time past time 100, so you can't do II plus 1 for length of time, right? So there is nothing beyond the length of time. So you have to go from 1 to the length of time minus 1. And so now I'm just going to plug in this equation. T of II plus 1 is equal to T of II plus delta T times the function that I just created, temperature of time of II comma T of II. And so this is the function evaluated at the current time and the current temperature. And so for the first iteration, this is going to be using the initial conditions, right? So my T of my next time step is equal to my initial time, which is 70, my initial temperature, which is 70, plus dt times the this function dt evaluated at time 0 and temperature 0. And that actually that will solve my equation. And so let's go ahead and plot this real quick. I want to make sure I don't need to change my end time. And so let me just copy this figure real quick, change these variables. So I'm going to plot time t, and then my y label is going to be response temperature in Fahrenheit. Let's see if this works. Wonderful. So actually, I didn't choose anything that was too crazy here, but as you can see, it kind of approaches 170. So let's start looking at this a little bit. So let's plot only to time 80, right? So 100 is a little too long. 80 will probably be a little better. There we go. And so let's find out what this maximum of t is. 169.996. And so the problem is that you can see the maximum of t is going to be t of n. So my last temperature, I want to see if that gets close to 170. It doesn't. So it's not, well, it gets close to it, but it doesn't actually equal 170. And that's because that's an asymptote. It's a exponential approach. And so what happens with an exponential approach is you get infinitely close to it, but you don't actually reach the number. And so I can make this go to times equal to 1,000, right? Like a really, really long time. And then you see it just goes up there and then looks like it's right at 170. Let's look at what my maximum of t is. It says it's 170. I can tell you it's actually not. But it says it's 170. So with 1,000, if I want to answer part A, right, is I want to use the find function to find when the time when it's equal, it's less than or equal to 170. So let me check real quick. So I'm answering the first part of this. So part A, how long does it take for the object to reach the bath temperature? I said it will never reach 170 in my answer, because if you use 100 seconds, which is a reasonable amount of time, it doesn't actually reach it. And so, but if you go to 1,000 seconds, it might actually reach it. So let me actually try to answer this problem completely accurately. So this is going to be part A. And so I want to find where t is less than 170, right? Because the next index I'm going to do in like my indices are going to be equal to find t is less than 170. And so what this will do is it will the last one will be the last number in temperature where it's less than 170. Let's run it. And so let's check. So let's find. So now with this find, I could do time of indice of n. So what this will do is this will tell me right here what time is the last time where t is less than 170. So that'll tell me when the temperature equals 170. Hopefully you all are following me. We haven't used the find function in a while, but again, I'm using the find function to find all the values where the index is, the locations where my temperature is less than 170 degrees Fahrenheit. And then I'm going to pull the time out of the last numbers, because that will tell me the last time where t is less than 170. And let's see what happens. The answer is 1,000. So it's 1,000 seconds. It took the entire time to get there. And so what that tells me is it never got there, right? So the answer is, because if it took 1,000 seconds, if it took the whole time, so if my index is all of my numbers, right? If you look, this index is every number, which means that t is always less than 170, then the answer is true. I confirm it. It never reaches 170 degrees Fahrenheit. And so that's the answer to the first part. And like if you look at my answer, it'll never reach 170. So I've proven that. I said even after 1,000 seconds, I've had it compare t to 170. And what it must be is that it must be infinitesimally off. So if you go t of n, it tells me that it's equal to 170, but that's probably because it rounded to 170. Because when I actually use the find function, it never finds a temperature that's greater than or equal to 170 degrees Fahrenheit. All right, so that's my answer to part A. So like I'll just put like a comment. It never reaches 170. All right, so now part B. is going to be the same thing, but I want to find where how long it will take for the object to reach 168 degrees Fahrenheit. So now I can use the find function for that as well. I'm going to use the same variable. It's going to be find where t is less than 168. And again, the reason I'm using t is less than is because if I use the last index, that's going to be the last time at which it's less than 168. So that's how long it takes to reach 168 degrees Fahrenheit. And so again, I'm going to output the time using the time of the last part of that index. So again, this index is going to be all of the positions, all of the locations that correspond to the same time vector as well, all the locations where temperature is less than 168. So the last one of those has to be the last part that is less than 168, because everything else is either greater than or equal to 68. So the last of those indices is how long, right? Using just logically, the last of those indices will answer this question: how long will it take for the object to reach 168 degrees Fahrenheit? And so now I'm going to bring this back down to 100. I want it to be a reasonable number. And right, so my first time is 100 because it never reaches 170. And then my time for it to reach 168 degrees is 39.1 seconds. So if I go up to about here, looks about right. 160. It should be around here, right? Yep. And so 39.1 is about right. That's how long it takes to get up to about 168. Cool. So now let me just put that in the comments. So it takes 39.1 seconds. That's my answer to part B. And this was part C. So if I were doing this and I were going to actually like go to publish it, I would create all these to be probably section breaks or something, right? And then I give my answers in the comments, just so that you can also see, if you're just looking at the script, you can see what the answers are. And so here's the plot of it. And so that's how you solve the problem with the Euler equation. So I'm not gonna solve for part A, part B, in part B again, because I've already found the answers. But what I want to do, and I've done that already for you in these answers here. What I want to do instead is I just want to show you how would you go about solving this problem using the ode45 built-in Matlab function. And so I'm just going to walk you through it from the start again. And so remember, this was the Euler equation, and this is going to be using ode45. Okay, so I'm going to need to do the same thing as before. So I'm going to show you again how I built this function. So this time I have to use a function. I have to give a function that I can use as an input to ode45. And that's why I was showing you already with the Euler equation that you should probably get into the habit of building a function to use for it, because it's just a little easier. It's easier to separate everything, so that way your solutions always look the same. So I'm going to build the same function. It's going to be this dt equals temp of t, comma t. So the derivative of t with respect to time is going to be equal to temp, this function that I'm creating that I'll use, of t comma t. And so that's the form that it has to be in, right? And so your function has to be t, y. It's basically the inputs here need to be the same as what your output of ode45 is going to be. So whatever that ends up being for your equation, in this case, it is dt is equal to t bath minus t over 10. And so now I can just write that in. I'm not going to use an intermediate step this time. I'm just going to straight up give my output is going to be equal to t bath, which is 170, minus t divided by 10. So this one actually isn't a function of time, but the problem is your ode45 is going to need this to be your form. It has to be time has to be the first input. The actual function itself needs to be the output. Right, the actual temperature, the thing you're trying to solve for, needs to be the second input to this. And so now I can just go and say, all right, so my output's time t are going to be equal to ode45 of, and now I give the function handle temp. This means to go use the function temperature. That's exactly what this means. I need to give my T span is going to be from 0 to 100 seconds. And then my initial condition is 70 right here. And now I'm going to steal my apply function. I don't want to have to retype all that. All right, let's see what I get. Oh, it didn't like something. dt was not assigned. Oh, so so this is saying. So if you haven't seen this before, this is saying output argument dt, which is this output argument here, is not assigned in my function file, or my function, in this case, subfunction. That's because I misspelled. So you have to remember, one of the basics of functions that I just messed up is your output that you're defining in this function, file or function or subfunction, has to be defined in your function. It has to be set as an output, otherwise the function can't be evaluated. So let's try it again. There we go. And that's the same response you see as the previous one. Okay, and so that's, I mean, this is, if I were to do this, the easier way is to use ode45. But on a test, I might have to use the Euler method. So you have to learn how to do both for just the first order differential equations. And so what I want you to do is I have another in-class problem for you. Following this same kind of pattern, I have an equation here that's defining the rocket's a rocket's velocity as it burns fuel. So the equation of motion for the rocket in vertical flight is given here. So your acceleration is defined by the force balance, right? So that's how you force F equals ma. And so your force balance comes out to be here, but your mass is given as a function of time because you're burning fuel, right? Your mass is changing. As you burn fuel, mass is leaving the rocket. And so this mass, m of t, is given by this function here. And so given all of these values, the initial mass, your thrust, the R and B values in here, I want you to use, so if you're listening to this, I want you to use either one. You don't have to use both. I'm going to use both when I go to solve it. Do either one. So this is, if you're listening and watching this, you'll have that heads up. I'm going to keep it this way because I do kind of always want to see who's actually paying attention to these videos. So choose one or the other. Your plot should look like this. So you should use 40 seconds as your time. And so from there, I will go ahead and solve this for you after I'm done with all these videos.